Decays conserve momentum, so one of the things that we know is that the momentum of the daughter nucleus is going to be equal in magnitude and opposite in direction to the momentum of the alpha particle. We also know that kinetic energy can be expressed in terms of momentum. So kinetic energy is equal to 1/2 mv squared. And one thing we can do is we can multiply 1/2 mv squared by the mass divided by mass. This is just equal to 1. We can multiply by 1. But then that means we can rewrite this as 1/2, and in the numerator, m squared v squared over m. So you'll notice here, this is actually going to be the momentum squared, and so kinetic energy is also equal to p squared, or momentum squared, over 2m. That's another way of writing kinetic energy. So if kinetic energy is momentum squared over 2m, and we know that the momenta of the daughter and the alpha are identical to each other, or they have the same magnitude anyway, we can figure out, relatively speaking, how much kinetic energy do they carry away. Now, the alpha particle is going to have a much, much smaller mass than the daughter nucleus. So if the alpha particle has a smaller mass, if m is small and momentum is the same between both particles, if m is small, then kinetic energy will be big. So the kinetic energy of the daughter nucleus is going to be smaller than the alpha particle. Alpha particle has small m, so big kinetic energy. So the daughter nucleus or the alpha particle is going to have more kinetic energy than the daughter nucleus. So the alpha particle will actually carry away most of the energy of the decay.